Next thing. Next thing is going to be are there any questions about anything? All right, so we're done with chapter 7, and now we're into chapter 8. And chapter 8 is about antennas. And Dr. Wentworth does this a little differently than most. He goes ahead and he starts giving you information about the electric field from antennas as if you knew it was there in the power radiator, without going through a derivation. I'm going to do the derivation formally, but first, I'm going to try to follow his method. So, if you have your book, and you turn there, and you turn to chapter 8, in the beginning, he gives you pictures of different antennas. We've all seen antennas. The most common is a straight wire antenna. It used to be called an aerial. It would be on cars and stuff, just a straight wire. Usually the antennas that are straight wire are about a half wavelength long. That's very typical because of some of the properties, the gain as well as the impedance and stuff like this. But they don't have to be. There are short dipoles that are short compared to the wavelength, and they work too, just not very well. Then there are antennas. The most common one you see out there are dishes, parabolic dishes that have a radiating element in the center that blasts energy and it scatters off the dish, just like a reflective mirror. If you've seen parabolic mirrors and stuff like this, or parabolic microphones. There are also square plates that are above ground planes that can be, they're called patch antennas. And there are slit antennas. As a matter of fact, with antennas, you can't say one or the other thing won't work as an antenna. Anything where you can develop an electrical potential across a voltage at a high frequency that has some conducting path back to the other side can potentially be an antenna. And I have a quick story about this. So antennas are used to really couple electromagnetic energy to devices as well as just radiate it all over. And long ago, there were waveguides. Then for some reason, somebody had a very narrow, thin waveguide that was very wide, that was the conducting waveguide. I don't know the reason for it, but I know they had it. And they needed some way to excite it. Now, the problem with that is if they just put a little filament in there, it won't excite it. Not well, at least. So they use what's called the genetic algorithm. These are algorithms that optimize something. They'll find out some solution of something that will give the best, you might say, performance based on requirements. And I'm using some words loosely here because it's a little tough. So anyway, they put a wire antenna, and there was a code called NEC. It was available. And they started this thing, and they put some requirements. This code could create a wire, thin wire, of any length with any number of bends, but it has to be a single strand. This would be an antenna. And then the outer part of the waveguide would be grounded. This would be driven at some voltage. And they cut a little hole in there so it doesn't electrically short out. So they let this program go to find something that would have the maximum efficiency in coupling energy or power to the waveguide. And it came up with something that looked like some nut just started bending a paper clip into a million different bends and zagged like this. And it showed, in fact, that it was an antenna that had the best coupling It's trying to impedance match this antenna. I'm not going to get into the impedance of this stuff because it's kind of crazy. So anyway, you look at that. There's no intuition that says that'll work. But they built it somehow. And sure enough, it worked. And they're like, don't. So then they asked it to do something where, and you'll learn how hard this is, to create a right circularly polarized wave in only one quadrant of space. There are 8 quadrants, 4 above the horizon, 4 below, each at 90 degrees. So it'd be in the positive X, positive Y, positive Z axis. Right-hand circular polarized. That's just about impossible, just telling you. Came up with this weird looking thing, looks like a paper clip with nuts with a billion bit, and sure enough, it did just about that. So that's when I got involved with optimization, genetic algorithms and stuff. And one of the things we do is use optimization algorithms to design antennas and other things for, and they're genetic algorithms. These are called global optimizations that are optimized in a statistically sense. It's really a probabilistic sense, weakly optimized. Anyway, we use these things, and I had a grad student, Dan Fairclough, that used them to design all sorts of things. But in order to use them, you have to know how antennas work so you can qualify the actual, it's called the metric or the performance. You have to find some figure of merit to talk about the quote goodness of your design compared to what you want. So that's where we're going today, but I'm going to just say this much. The beginning of Wentworth's book assumes we know the electric fields or the power radiated from an antenna, and he goes through some designs. I hope you don't lose power. So let me just tell you this. I got some notes down here. This doesn't apply to straight wire antennas, but when we have aperture antennas, these are antennas that have some area, like a parabolic dish, a plate, something that has an area. It's not just a thin wire. Y'all follow me? When we have an aperture antenna, Mark, we talk about something that defines a distance called the far field distance. So I'm just going to draw an aperture antenna. This is my rendition of an aperture antenna. It's an aperture antenna as such. It has width W, height H. And the key thing you look for with apertures is the maximum dimension. And that's called L. In this case, L would be equal to the square root of H squared plus W squared. It's the dimension where if you look at the aperture, the longest distance you can go inside that aperture from one end to the other. For a rectangle, it's the diagonal. If it's a dish antenna, it would be the diameter. You with me? Elliptical antenna, it would be the major axis. That's what it comes down to. And when you have that, if this is my aperture antenna, this is my antenna, there's a distance that you have to be beyond before you can assume the electric and magnetic field are in the far field. Now, I think we talked about far field, so there's some distance R, and R has to be greater than or equal to, actually greater than, all right, 2 times that dimension that I'm calling L squared over lambda. And lambda is simply the wavelength. So R has to be greater than that to be in the far field. He doesn't justify this or verify it. He just states it. He's right. We're going to justify this for a thin wire. I don't think we do it for an aperture, but if we have time, we will. Antenna. Anyway, so just you think about this, okay, that's well and good. What does it mean in practically speaking? This is R, by the way. It doesn't look like an R, but it is. And this is for the far field. We have to be beyond this in order to be in the far field. So what would it be for something that's reasonable? Okay. So if we have a dish antenna, let's assume the dish antenna has a diameter equal to 1 meter. That's not that big. You've seen those things on your roof. I have a dish antenna on the roof where the house I live. It's been there since we bought the home. I've never had satellite TV. I'm thinking about it now that from what I've been told, satellite TV, you get, does anybody have satellite here? Well, you get a cajillion channels, a lot more channels, especially international channels. My wife's Chinese, and she likes tennis. Here's the thing, French Open's going on. We see we get ESPN, we see snapshots of tennis. If you get these dish, I mean, really, it's amazing. You get everything. I mean, you probably find a channel out there that's got it on there. So just remember what I'm telling you. If possible, before you just sign up with a cable provider, you want high-speed internet, who's ever the cheapest. But then see if you can get satellite TV for a reasonable price that has a cajillion channels. Because I'm telling you, we get Spectrum. Do y'all have Spectrum? Or what do you have? Up north, they have like 3 or 4 cable providers. Up in Huntsville, I think you have Cox, you have several others. Here, I think we have Verizon buried cable in some areas, but I don't know if they give internet there. And there's YouTube TV and stuff like this. Anyway, I'm just going to tell you this much. Satellite, generally, you get an enormous number of channels for relatively a low price, where cable, it's very defined, limited amounts, just for your information. Back to this thing. 1 meter is about the dish on your roof, all right? So let's assume, and I just came up with stuff, the frequency is 1 gigahertz. Yeah, sure. We're assuming it's 1 gigahertz. It's actually a little low. So now it'll be, I'm not sure what the satellite uplink is actually. Anybody know what the uplink, downlink frequencies are? Wi-Fi around here is 2.45 gigahertz. I think it's a lot greater, but I don't know exactly. I think it's going to be like 30 gigahertz or 40, but I'm not certain. I got to be careful about it. So anyway, if we take a look at what that distance would be, that means I have to be greater than 2 times 1 squared over the wavelength. Well, the wavelength's 1 gigahertz, so it'd be 10 to the 9th. I mean, if we talk about wavelength is C over F. So C would be 3 times 10 to the 8th over F, and F is 10 to the 9th. So it'd be times 10 to the 9th. So that's going to be 2/3, or about 6.6 meters. It means in order to be in the far field, I got to be 6 meters away. Now the thing is, you see how as frequency goes up, you have to be further and further away. Y'all see that? Which is not true with a wire antenna you're going to see. It's actually inversely proportional. It's wavelength over 2 pi. This is for an aperture antenna. If you had a wire antenna, we'll prove this too. For a wire antenna, straight wire antenna, of length L, your distance here that you have to be greater than to be in the far field is R simply greater than lambda over 2 pi, which is completely different, because then as wavelength goes up, you can be closer and closer. We'll prove that one, all right? Not right now, but we will. So anyway, when you talk about this, I'm already saying that Dr. Wentworth is going to give you the electric field, or he's going to give you the H field or the E field, and we're going to calculate some parameters that I'm going to introduce you to today. Things that are called, I call figures of merit. You have a question? No. Figures of merit. They're ways of more or less talking about the, quote, goodness of the antenna, lack of a better term. So, we know what the far field is, and we're going to assume we're in the far field when we're talking about the next bunch of stuff, because it makes no sense to talk about it if we're in the near field or close to the antenna. So, if we, by the way, what is the far field, near field? What does that distinction mean to you, anyone? I think I told you, didn't I? Well, I'm going to, if I have. You know when you have a capacitor, if you just put a voltage on a capacitor, you get electrostatic field lines around it, right? There's nothing, it doesn't have to change with time, it can be static. And there's energy in those fields, right? The energy in an electrostatic field, the density is 1/2 epsilon E squared. Well, that energy is not radiated. It's not launched. It's there resident. I thought I talked about this with plane noise. Now you can get that energy out if you put a resistor across that capacitor. All that energy that's in that field, it will dump back in into a current. In short, all of it would be equal to the integral of I squared R dt, all right, from say 0 to infinity. You can get all that energy out. If you have an inductor, just a coil of wire with current in it, there's an energy in the magnetic field. It would be, energy density would be 1/2 times mu h squared would be everywhere, or 1/2 Li squared would be the total energy. Do y'all remember that? 1/2 Li squared. You can get that out if you put a resistor across there instantly. All that energy would dump into that resistor. Okay. Now, that energy isn't launched. It's in the field, it's resident. When we talk about propagating fields, the electric and magnetic fields are launched. They're perpendicular to one another, and the electromagnetic photons are propagating away. Didn't I give you this lecture about photons? I thought I did. Photons are what make up a propagating electromagnetic wave. They're real. The near field energy is called virtual photons, and I'm not going to get into this because I really don't know it that well. But propagating electromagnetic energy, the photons don't have any mass. That's what light's made of. But they do have momentum, which is kind of an oxymoron. How can that happen? Because momentum is what? Mass times velocity, right? But in the limit, as the velocity goes to the speed of light, then those photons get something called a rest mass. And I'm not going to go there either, but it's 0. It's tending to 0. But the product is going to about. Anyway, that's for another time. So, that said, we're talking about launched photons. We're talking about far field related to that. Now, based on that, well, we know this. If we have a far field, a plane, let's even do plane wave. Plane wave in the far field. Actually, this is true for propagating fields. We know that H is equal to 1 over the intrinsic impedance, AR, the direction of propagation crossed into the E field, and E would be minus eta AR. That's the unit vector in the direction of propagation crossed into the H field. You all remember those little tricks, right? That's for propagating fields, not near fields. If I have that, I can also say that the average power density would be equal to 1. This would be a time-varying phenomenon at constant frequency. 1/2 the real part of E crossed H conjugated. And that's really just something that's the scalar average power density times AR. We're assuming AR is a unit vector in the direction of the energies propagated. Y'all with me, class? All right, and then finally, this is Wentworth's book talks about this. Finally, we can say that the total power radiated, this is important right here, we'll call it, to be consistent with Dr. Wentworth's book, P rad is equal to the integral of the average power density. That's a vector integrated over a surface that encloses the antenna. This is going to be a surface that encloses that integral with the 0 in the center there, that just means a closed integral. It's a surface that you can't get out of without punching a hole in it. It's a closed surface. All right, then he gives an example just to get us a little more familiar with this. Suppose I give you H equal to IS, I'm going to make a comment here, over R. This is going to be in spherical coordinates, radial distance R, sine of theta, a phi And I don't even think, does he put down the, he doesn't put this down, but it should have, this should be there. E to the minus j beta r should be there because it's propagating away, put that in, away from the actual antenna. The e to the minus j beta r tells me the thing's leaving, propagating away. Here's something to note. With propagating electromagnetic fields from antennas, if they're in the far field, the E field and H field vary as 1 over R. Remember that. If you saw 1 over R squared term there, that would be a near field. Okay. It's 1 over R, 1 over the radial distance from the antenna. Everybody okay with that? All right, now that's the H field. Some of you know, well, I can get the E field just saying, well, it's propagating at R. The H field's in the phi direction. So I know E cross H is the direction of propagation. If E was in theta, it would be in the right direction. Theta phi, theta cross phi would be R, right? Do you all remember that? All right, so I could just look at that and take that H field divided by eta naught, right? And then put it in the theta direction, and I would have the right value for the electric field. Or if I didn't feel good about this, I could say, well, the E field would be minus eta AR crossed into H. And if you do that, well, I have R, yeah, that's right. R crossed phi would be minus a theta with the minus sign is plus. So it would be eta times IS over R times E times the sine of theta times e to the minus j beta R, and then it's going to be in the A theta direction. That would be the E field. And to get the power, if you're watching in your book, you can see that I added that thing for a reason, because that wasn't there, and you can't do this without it. So then when I get the propagating electric field, or the power density, P-av, that's going to be 1/2 the real part of E cross H conjugated. And when you do this, I'm just going to tell you how I do this. I know there's 2 ways to get the amount. This is a lossless system. There's no e to the minus alpha R. I know it's lossless. So I can do it 2 ways. I can say, well, it's a propagating wave. That's the power density, 1/2 magnitude of the E field squared over eta. Or I can say it's 1/2 times eta times H squared. Either one will do the same thing because E and H are interrelated by that. So I'm just going to say it's going to be 1/2 times eta. That would be the atmosphere's eta naught, probably. In fact, I want to put it as eta naught. 1/2 eta naught times this squared. So it'd be IS squared sine squared of theta over R squared. And the phase term goes away and would be in the AR direction. Put it small r. Now that would be the power density in watts per meter squared of the field that's propagating. And yeah, that's what we have, and that's what he has. This is drill 8.1. And then he asked for the total radiated power. Now, I want to do this part because this is important. So that's the power density, right? Watts per meter squared. How do we get the total radiated power? Well, we integrate that over the surface of a sphere, right? So just watch this. You're going to see a lot of stuff drop out, but just watch. So to get the total power radiated, I know it's going to be a double integral. This is over a spherical surface holding R constant. That's going to be this stuff right here. So I have IS squared times eta naught divided by 2. That's a constant. And then I have 1 over r squared. And I have sine squared. And then it's in the AR direction. That's simply rewriting the PAB, right? You all with me on that? I'm just rewriting that there. Now, I got to take ds. This is going to be at a constant radial distance. So it's a dot product of ds. If you're on the surface of a sphere at a constant radial distance, it's in the AR direction. And the surface area, the differential surface area, will be r squared times the sine of theta times the theta d phi. How many remember that, by the way, for the differential surface area of the sphere? R squared sine theta d theta d phi. This is holding our constant. I can show you that if you need it. All right, now, theta will go from 0 to pi. Where does phi go, everybody? If it's a closed surface. From x-axis is 0 all the way around back to the XOR, 2 pi radians, right? One thing you're going to see right away looking at this, AR.AR is 1. So get rid of that. Now, you see how the r squareds cancel? If I got something that's a function of r, I messed up. The total power leaving an antenna has nothing to do with the radial distance the shell is you're looking at that it's penetrating. So I see that r squared goes away. Then I have sine squared theta, sine of theta. I'm going to do this once. So this is p rad, and this is equal to the integral from 0 to 2 pi, right here. Matter of fact, let me do it this way. Is that random here? Yeah. Would somebody just mind telling me how long it's going to go on for? I hope they know. So I'm going to take this constant out in front.
Starting at 3 is a 40% chance.
3 o'clock?
It's 100 at 2, and then at 3 and 4 it's 40, 30, and then nothing at 5.
Let's hope we're right. Last night, I don't know if you guys have this. I got these AU alert things on my phone.
Yeah, man. Oh, like 3.
Oh, man. Beep, beep. So one went off about 11 or something like that. Then one at 12, then another one. And then it started thunderstorming. So I got a dog. Dog gets scared. I don't know if I got to bed before 2 and fell asleep or not. But, and then I got woken up again, I think, in the morning by something. Did it rain twice last night? Once early, one late. I mean,
I think so.
it was not a good night for me sleeping. My wife slept through the whole thing. She wears earplugs. Anyway, I messed up. So that's the constant out front. Now I have these integrals. I have from 0 to 2 pi and from 0 to pi. And I have sine cubed theta, and then I have d theta d phi. Now, I'm going to just tell you, I do this because this, believe it or not, is an integration that people will mess up. Now, you have symbolic integration on your calculators, don't you? A lot of them do. I don't know. I think the 93 does it, and that, is it Inspires, one of them? I think it does it, but I'm not sure. So first thing, I get rid of everything I don't need. You see, when you integrate d phi, there is no phi, so it just becomes phi from 0 to 2 pi is 2 pi. So I know I can put down 2 pi eta naught is squared over 2. I just got rid of that d phi integral. Then I've got this integral from 0 to pi of sine cubed. You guys remember how to do this? I have to do it a lot, that's the reason I don't do this. Well, you break sine squared, or sine theta out into sine squared theta times sine theta, all right? But sine squared theta can be 1 minus cosine squared. So I do this, I say, this is equal to 1 minus cosine squared of theta times the sine of theta. and it's d theta. Y'all with me? Now this is a u du thing. All right, so the first one, and I'm just going to tell you this, when I integrate from 0 to pi of sine theta, I get cosine theta, don't I? Minus cosine, don't I? Remember, the derivative of sine is cosine, integral of sine is minus cosine, right? Oh, minus cosine theta. Well, minus cosine theta is pi is minus 1, right? So I get minus a minus 1 or 1, and then it's minus a minus or plus cosine of 0, which is plus 1 or 2. So I know this whole thing is going to boil down to, let me do it this way. This number is pi eta naught is right here squared. And then the first integration is going to be just 2. I know that because it's just integral of sine theta. The second one, well, what's that going to be? It's the integral of minus cosine squared sine theta, right? Well, if u is cosine theta, then du would be minus sine theta d theta. Do y'all agree with that? So this is real, because there's a minus sign, is just going to be equal to a u, take a look at that, u squared du. Now, if u is cosine theta, y'all know what I'm doing here, right? If u is cosine theta, then when theta is 0, cosine of 0 is 1. Y'all agree with that? And then, since u is cosine theta, when cosine theta is pi, it's minus 1. So I need that integration, right? So what is that going to be? Well, what's the integral of u cubed? I mean, u squared, it's u cubed over 3. Evaluate from 1 to minus 1, right? So I can take and flip these limits and put them, well, actually I can just leave them alone. So I have minus 1 cubed minus 1 cubed over 3. And let's see, that's minus 1 cubed, which is going to be minus 1 minus 1 cubed, which is minus 1. So it's minus 2/3. So it's 2 minus 2/3 here. I'm maybe doing this a little casual, but I think you can appreciate what I'm trying to show you is just evaluating that integration. So I have 1 minus 2/3, right? Or 1/3. Y'all agree with that? So that means it's going to be pi over 3. Or wait, sorry. This is 2, and this is 2/3. So 2/3 is actually 6/3. My bad. Minus 2/3 is 4/3. Right? My bad. So that's 4/3 pi eta naught right here. Is squared is the total power radiated. Let's see how Wentworth's book, what it says. And in Dr. Wentworth's book, he has that. So that's how you do it. But again, he's just integrating the total power radiated over a surface. Don't let this kind of stuff trip you up. You can look up these things, of course, but just realize substitutions work for a lot of these integrals. Or use your symbolic integrator. A lot of you have. So next, after that, we're going to talk about something called radiation, power radiation patterns. These are important for a lot of reasons. I'm not used to talking to a class this small in this room. When we had signals and systems, you had me, didn't you? Didn't we have a whole lot more people?
We were in the small room downstairs.
Oh, anybody in here with me for a class? I'm used to having like 60 people, 70 people in here and getting a lot of questions. Maybe it's summertime and does it seem humid in here?
Mm-hmm.
I just feel, I don't know what the word would be. I feel a little warm, a little humid, and after last night, a little tired. I'll tell you one thing, my phone is not gonna be near me at night from now. Neither is mom's. That thing, does anybody remember when the last alert came through? 12:30. Well, after that, we got a storm where I live. I live out in Grove, I live out in Morris Mill Road on the golf course off Holston Street. And after that, then thunder, then the dog. Just I'm scared. Then there's peace at about 2 till about 3:30 or 4. Then more thunder. And I was like, you know what, I'm gonna wear earplugs, put on white noise, lock the dog out, do something. That was not fun. All right, so now in chapter, the next part of the chapter, he talks about beam patterns. Then we're gonna talk about directivity. This is real important. When we have any antenna, why are we using it is the first question. The reason we're using is it focuses electromagnetic energy in a direction or power, or because the transmitting pattern you're going to see is the same thing as the receiving pattern for an antenna. So just think if you have a light bulb, but you want light to be focused, you'll probably get a reflective surface behind it that makes a parabola, right? And that way it'll reflect all the light in a certain direction. Well, that is a form of an antenna. It's focusing the electromagnetic radiation into a direction. Now, an isotropic radiator, iso means equal, and isotropic, equal in all directions radiator, is one that radiates in every direction the same amount of electromagnetic energy. An approximate isotropic radiator would be a star or the sun. Right? Even though it's really optical like we see, it's the sun emits over the entire radiation spectrum. The microwave up to ultraviolet and gamma ray and stuff like this. And it goes down much further in frequency. So the sun's a good, when you think about an isotropic radiator, that's what it is. But when you have an antenna, what they talk about is the power pattern. Now, remember last time I showed you that the actual average power density was equal to eta, this is for the prior example, squared, right here, and it was divided by r squared. Then it had an angular variation of sine squared of theta, right, like that, and it was in the AR direction. You can look. And that was the average power density. Y'all remember that? Now what they always do when they take a look at a power pattern, normally at least, what they're going to do is normalize it to its maximum possible. This is the average power density versus angle, all angles, we're given R. So what they do when they talk about the power pattern that they're going to plot, they do this. They simply say, we're going to plot this quantity, and I'll just call it Pn, P normalized. And that's the magnitude of the average power density. It's a function of angle. Call it the function of angle here. Over, they're going to plot the average power density there versus the maximum value of the power density. Now, I'm going to tell you why I'm saying that. This, you can say that R is held constant for this. And here's why. If you look at this, the maximum value of this would be when the sine of theta is 1, right? At theta equals 90 degrees. Do y'all see that? Theta equals 90, it's got the most, and the value would be 1. Well, at that point, I have eta is squared r squared downstairs. Then it's divided into that. The only thing left is the angular function. So you're left with simply the sine squared of theta. Take a good look at that. If we normalize to the maximum power density, and this is how it's normally done, this isn't that important that you understand every intricacy, but understand For this one, the maximum possible value is going to be 0. It's going to be 1, right? Now the minimum value is 0. Now we plot that versus angle. And I'm going to do it the way it should be done. That, by the way, I'm just going to say this. We use polar plots. And y'all know what polar plots are, right? They're not going to be linear where you just have angle, even though Whitworth's book may have an angle versus magnitude. What we do is polar plots. So this will be the z-axis right here. And the length of the line from the origin is proportional to the value of the quantity you're plotting versus angle. So our angle is going to be measured. I'm calling this theta. Right? And it is measured from the z-axis, if you remember, right? So for that, by the way, that pattern right there, that's for a short dipole. I'm giving it away, but so if I plot sine squared theta, start at 0 when you're going straight up, the length of the line would be 0, right? Sine is 0, 0. Well, as I go out, the line gets longer and longer, and I get this. I'm going to get this. Basically, I'm going to get a shape that revolves around the axis because it's not a function of phi. And the maximum value will be when this angle theta is 90 degrees. Y'all with me? So that's the radiation power pattern normalized. Now, sometimes what they'll do is plot this in dB, and they'll have it versus, then it makes sense to do it logarithmically. And they'll have the power pattern right here as a function of angle, the average power, and it'll be normalized to P max, but it'll be in dB. And you'll see stuff like this. It starts at 0, so it's coming in from minus infinity, and then it's doing this. It monotonically increases and hits a maximum here of 1. Well, the log of 1 is 0, so there'll be 0 dB. And in Whitworth's book, if you look, he's showing you what I'm showing you, only a little differently. This is on he doesn't do this for the actual power density I do, but if you look at the bottom of page 430, how many other books are access to your books? Y'all have it? You want to look at page 4? Do you have one or not?
I have one.
I mean, you don't have to get it out, but at the bottom of the page, he's doing what I'm showing you. All right? He does it logarithmically, then he does it with a polar. The polar plot is the one we use a lot, mainly, because it tells me as a scientist and engineer, if I got an antenna system and I want to see how much of this power pattern without doing any, any kind of formal calculations about percentage of energy or power in a certain quadrant, if I want to see how much is going out there, I take a look at these patterns. They're usually 3D, by the way. You get these lobes. And I can tell right away if that thing's doing what I think it should be doing. And if it is, then good. But if it isn't, then I need to correct it. So those are things that these are antenna power patterns. And they're important. Now another thing, and this is important that we do, is we get the actual, we talk about something that has to do with the amount of focusing ability the antenna has, and that's called the antenna gain, or the directivity first, but then gain ultimately. So I like to talk about this. And just think about something. If you have anything, like with telescopes and stuff, the figure of merit you use is the actual magnification power of 10, 20, stuff like this. With antennas, when we talk about directivity, that's how much better it is at putting a maximum amount of power density in a certain quadrant of space, better than isotropic, right? So I'll try to do this in a way so you'll understand the reasoning behind it, not just give you formulas. I'll tell you one other thing. I'll try to show you as much practical stuff about antennas as possible. I designed a few, and I had some crazy stuff happen, or unexpected stuff. So now the next thing is directivity. Please write this down. The symbol for directivity is D, and that's unfortunate because that's also the symbol for diameter in a lot of places. But it's D. That's directivity. It's unitless. Could be 0, actually 0 dB, but it can't actually be mathematically 0. It can be 1. And what is it? Well, the directivity is equal to the actual power density, PAV, that your antenna has as a function of phi and theta, versus what an isotropic antenna would have. So I'm going to just say this, hold R constant for this one, so R is a constant. Well, I'll try to make this more real. I know that the power density for any antenna, it's going to be in a lossless environment, or it makes no sense to talk about it, a pretty low loss environment. That's proportional to, I mean, that is equal to 1/2 epsilon, or 1/2 eta, or 1/2, sorry, E squared over eta. Well, if I think about the average power density, it's also going to have an E squared in it, right? So a lot of times what they'll do is say it's really equal to the electric field that I actually have as a function of theta and phi squared over the electric field I'd have if I had an isotropic radiator radiating the same amount of power. One thing that's constant is the power. Y'all see this class? If I put in the etas, they'll cancel, the 1/2s cancel. So I just put the E squared. And the thing I can do is say it's equal to PAV right here of the antenna I'm using as a function of angle. Well, the isotropic power is really P rad. It's the total radiated power over 4 pi. That would be the average power density for an isotropic radiator. You'll notice there's no R in that one. Normally it would be P rad over 4 pi R squared. But we're putting R equal to a constant, and it's better to say R equals 1 meter, theoretically. Don't worry about that. It'll always cancel the R's. All right. Now, I can go ahead and do the development the way he does it, or I can just tell you sort of the answer here. And in his book, he's going to do this on page 433, but he doesn't do it the way I like to do it. So I'm just going to tell you, I'll just tell you this. This whole thing for directivity, write this down. The directivity of an antenna, this is the easiest way to calculate. It will be, this is going to be the maximum directivity, by the way. He doesn't state this, but call this D max. This is maximum directivity. It is equal to 4 pi divided by, and it's the integral of the normalized power density as a function of angle. There is no R here. All right, just think about R equal 1. I can put an R in, but it's going to cancel. Dot ds. So it's really that ds, since R is 1, it will just be sine squared of theta d phi. And that's the reason I did the d theta d phi integral with a sine squared at the beginning. So it's going to be normalized power density just times, this is a scalar quantity. It's radiating outward times sine squared of theta d phi. And theta will go from 0 pi, and phi will go from 0 to 2 pi. Now, I'm going to say this. Dr. Whitworth has this spelled out. Well, he doesn't do it, though. He didn't write it down. He didn't break it out. But if you look at equation 8.16, right there, and then just take equation 8.12 and stick it over there, that d omega, I wish you didn't put that in there. That d omega is sine squared theta d theta d phi. He actually shows that on equation 8.11. It's a differential surface. All right, it's called a solid angle. And it's a differential surface in stair radians, but don't worry about that. Just put down this. This is the one you want. That's D max. I'm not done. Because here's where it gets good. So big deal, it's D max. What good is it? Well, first, the higher that value, the higher the focusing ability of the antenna. So the better off you are focusing energy in a certain power in a certain point in space, all right? Directivity is always used this, but really, the thing I like to think about is something called gain and directivity. They're linked. And write this down now. He doesn't do it, but I'm going to tell you it's better to do it this way. The antenna gain, symbol for that is G. And G is really equal to the efficiency of the antenna times the directivity. Now, I mean times D, right? Well, the efficiency, this is the efficiency. Efficiency is something that's going to be between 0 and 1. Typically, it's 100% would be a value of 1. Typically, it's like 0.95 or better. Most of the time when you talk about gain, you're talking about directivity. If you're talking about directivity, you're talking about gain. Y'all with me on that, guys? Here's where it gets important. Pay attention. So, you know, one of the things is, well, what could cause the efficiency to be less than 1? Ohmic losses. Anytime you have current in wire, and if you have a wire antenna, you're taking some of that power and it's heating up that wire, and that means there's power loss there. Y'all follow me on that? So that would do it. Another thing that will do it has to do with things where you get corrosion and stuff like that, and then you get an inefficient coupling of the power available to the antenna. You'll have, for instance, you all know with transmission lines and stuff like this, if you don't have the impedance of the load equal to the impedance of the transmission line, then you get reflected energy and it's bad, right? So you get something where you get that reflected energy is real bad, and it can really cause problems because you got all this power and stuff like this you're sending, but you're only transmitting a little bit. So here's my story. I have a personal experience with this. Now, you know, when you talk about reflected energy off of something or reflected power, one of the things that they talk about is the standing wave ratio, right? Do y'all remember that back in waveguides and stuff, or back in the day of when you had that transmission? Oh, well, you wanted the standing wave ratio to be 1. That means nothing's reflected, because standing wave ratio is the maximum voltage over the minimum voltage on the line when it's at steady state. You want it to be 1. You want the reflected. It's really the maximum value of the voltage over the minimum. Well, if the minimum is the maximum, there's nothing reflected. You don't get any kind of a standing wave pattern. And I designed an antenna when I was working for NASA as a consultant in the summer. As a summer faculty. Wait a second, was that a fellow that year? I don't remember. Anyway, yeah, I think I was, but I'm not absolutely certain. So we designed an antenna. It was to be used, this was sort of a smaller subscale antenna to prove a point. And what the antenna has had 3 arms, all at 120 degrees. It was just, you know, think of a, just 3 arms at 120 degrees and 100 horizontal plane. They had dish antennas on, or not dish, they had, it's called shorted annular ring patch antennas that were for a very specific purpose. And what they wanted to do is have this focus of beam. This is called a thin antenna. Each antenna theoretically had 8 arms straight up. However, it's going to be used in space, so it would be pointing at the Earth. But the antennas can undergo deflection. You've got to understand this happens. And if it deflects, they want an algorithm that would predict first how the pattern would be degraded and then ultimately how you could correct it, more or less give it glasses. Do y'all remember what happened back in the day when they had the Hubble Space Telescope? Does anybody remember this?
The wrong.
Have you heard of the Hubble Space Telescope? What was that?
They had the wrong units for what they measured the curvature.
Here's what happened. They got a mirrored surface. This is a reflective telescope. It's designed on Earth. That means the force of gravity is perturbing the mirror. So they didn't take into account how it would adjust or recurve when it went into space. So they launched it. It takes a lot of money to do this. Launch this thing up in space, and the images they're getting are blurred. This is what happens when all of a sudden you don't hold people accountable, because they just want money, these contractors. Trust me on this one, I know a lot of them. I mean, the good contractors, they do a really good job. They won't let, because they're proud of their work and they want to make sure they keep it. Anyway, they didn't consider that as a problem. So what happened is, as this, I don't know, maybe $1 billion project is orbiting, and it's supposed to give these incredible images of deep space. It's not. So what they have to do is create an algorithm that will adjust the images. It'll do basically image processing in real time that will have the phase corrections for the deformed image or deformed lens. And this was a monumental task, but they did it. It's electronically done. It was amazing they could do this. To me, it was amazing at least. So anyway, then they could get very sharp images. They had to give it glasses. Well, mine didn't have that problem. I designed this antenna theoretically to work perfectly. And I had the right thing, impedance matched it, should work. Sent it off to be built at Ball Aerospace, to be tested at Ball Aerospace. I forgot. There were contractors up there that built it. Now remember this much too. This is a lesson to you. Anytime you hire contractors to do something and technicians, don't assume that they appreciate everything about the problem. If they're there to solder, a lot of these people are hourly workers, they solder. They're not told how big of a solder ball to leave or anything. They just solder. So my antenna goes to Ball Aerospace, a lot of money, and I wasn't there when they tested it. So the technician there calls me up and goes, you've got a standing wave ratio of 4. Yeah, it's really crappy, This thing's never going to go here. So, and I got an idea. With your permission, I'm going to go in and take a look and see what's under the underside of that. So you got to understand, this is a planar antenna. It's got things here, things here, things 3 link. But underneath it was connected with a coax cable. Should have had no problem. So he starts opening it up and he sees this huge solder ball. Now, it was a 1.4 something gigahertz driving frequency. But 1.4 something gigahertz, that solder ball had a lot of impedance. It had a lot of reactance, like of the order of 70, 80 ohms, and that sucker was causing. So he called me, and this guy thankfully was an electrical engineer that's doing this stuff. He's a real deal. And he says, I think I can remove it. Go ahead and do it. And he does it, and it gets rid of the problem. But man, talk about realizing your reputation was just shot for good. He figured it out. Thankfully, we got the thing working, and the measurements were done. So the moral of the story is the efficiency on that was horrible. That's this number here because of the standing wave ratio problem. It might have been like only 50%, some 0.5, which is so unacceptable you'd be thrown out at NASA. If you were a civil servant, you'd design something like it. But I learned a lesson about that. From now on, anytime you do real tests, you show up even if you pay people to build the thing. I remember that lesson. And that's how efficiency works. And that's my story. It's a long one, but it's worth it. So now, why directivity or gain? Let's assume we got a very efficient antenna. Take this down. This is the reason it's so good to know. We'll do the calculation, but here's why. Whitworth doesn't talk about this stuff. So remember, directivity and gain talk about how much better your antenna is than an isotropic antenna at focusing energy, right, or power. So if you have an antenna, please write this down, it's done in the book. If you have an antenna All right, and I know it's radiating a certain amount of power. We're gonna assume the efficiency is equal to 1 or 100%. In other words, there's no inefficiencies. And that means directivity is equal to gain. Okay. So if I know how much power I'm radiating and I know the gain, so I know the gain is a function of theta or phi. It will only be a function of theta or phi, not r. Y'all with me? Then, if I want the power density at any given angle, theta and phi, I'm only going to show you theta. If I want the power density here, the average power density radiating away from the antenna, assuming it's at the origin, this is far away, then what I can do is assume it looks like just an isotropic radiator to start with. Well, if it's an isotropic radiator, it means the power is radiating equally well in all directions. And if I want the power density, I just take the total radiated power and divide it by the surface area of a sphere, or 4 pi r squared. That would be the isotropic power density. Y'all agree with that? Surface area of a sphere is 4 pi r squared. Then you would multiply it by the gain. And you would have how much better it is, or worse in terms of the directions you don't want, than an actual isotropic radiator. And if you went ahead and took that as your average power density and normalized it, trust me on this one, and you went and cranked it into the 4 pi over the integral of the average power density over the surface of that sine squared theta d phi, you in fact would prove that the gain was equal to the gain right there. I'm just going to tell you it happens that way. Now, I'm not even going to bother doing it. So that tells you how gain directly affects, if you know the gain of an antenna as a function of it, then you can tell the power density anywhere, all right? Now, the first step we do in this thing is actually do a few gain calculations for typical antennas, okay? And the first one we already did it, that was the one in Whitworth's example, was the sine of theta was how phi was, how h was, excuse me, h was a function of sine of theta. And we proved there that we actually found the normalized power pattern was sine theta. Do y'all remember that? Now we're going to find the directivity for that. So let me go back. This is the first example. I guess it's 8.1. Drill 8.1 in this book. And we're going to find the max gain from that antenna. So this is drill 8.1. Correct me if I'm wrong, I believe it is, right? So here we know the normalized power density will just be sine squared of theta. That's when you take the maximum and divide it into the actual power density. The maximum we found out would be was sine squared would be 1, right? You don't remember that? So that's the normalized power density. Y'all with me on this? Now I'm going to find the maximum directivity. So for this one, d max would be equal to 4 pi over the integration, all right, of this, which is going to be sine squared of theta times the differential surface, which will be sine theta times d theta d phi. Now, I want to tell you, he shows you d omega on page 431, equation 811. That d omega goes into 812 to find its capital omega c. It's used in equation 816. But I lumped everything down into, that was P normalized, remember that? Times sine theta, d phi, right? All right, so what's this going to be? Well, theta goes from where to where? If we're over a spherical surface, theta goes from North Pole to South Pole, or from 0 to pi, right? Now where does phi go from?
0 to
0 to
2
2 pi. I say this over and over again so you don't forget it. Now, luckily, we just did this one. I don't know if you remember, but we just did it. So when I integrate the d phi, we have 2 pi. I'll let you catch up. We integrate the outer one, d phi, we get 2 pi, don't we, guys? Right, so we just get 2 pi. Now we integrate the inner one, that's sine cubed of theta d theta. Y'all remember how to do that? What it is? What was the integral of sine cubed of theta d theta from 0 to pi? The bomb is late today. Anybody remember how to do it? Sine cubed becomes cosine squared, right, times sine theta d theta. Let u equal to cosine theta, right? I mean, sine cubed becomes sine squared, which is 1 minus cosine squared of theta. Sorry if I said that wrong. Times the sine of theta. Anywhere when you do this, this whole 9 yards comes out to 4/3. Y'all remember that? Trust me on this one. So this is going to be times 4/3. And lo and behold, you see the pi's cancel, right? The 4's cancel, and I get 3/2 or 1.5. And then I'll tell you this. That is the gain. I'm sorry. That's the maximum directivity of a short dipole. I'm just going to say that. This is about as low as it gets for any kind of an antenna that's used today. Now, there are isotropic radiators or things that are a little more isotropic that are used. Here's why they're used. Think of your cell phone. See, I mean, this antenna, it's got kind of a dumbbell shape, but it's putting all its power out in the horizontal axis, right? But if you're a cell phone user, what you would like to do, I mean, if you're a cell phone, if you run cell phones, you would like to have your antenna just give a footprint on the ground only of the energy, no energy up, right? Y'all with me on this? That's what you'd like. Well, there's ways to do this with patch antennas where you get these big footprints on the ground, and with cell phone towers, a lot of them have patch antennas for that reason, and we'll get to that. But they're trying to get the power distributed over a very broad, I mean, enlisting over a very broad area where there'll be no holes. So they get very low gain, but they're very focused on the bottom part. But generally speaking, 1.5, it doesn't get any less than that, even though maybe in some cases you can get a little less, not by much, okay? Just bear with me on that. So that's the max directivity for a short dipole, and for that one, I'm almost out of time. You guys got 226 roughly, 225?
Yeah.
I'm gonna do a few more things. With these things, Wentworth shows you how you can plot antenna patterns, and he shows you some typical antennas. And I mentioned about its efficiency. This is section 8.14. I don't spend a lot of time on that here. I do after I introduce you to antenna, how to calculate the fields from antennas. The reason I don't is because copper losses are really a function of the amount of current. And the amount of power radiated has to do with the radiation resistance of an antenna. And that's something we have to calculate. So now if you look in section 8.2, right away he talks about electrically short dipoles. And reading that section, you will be baffled because he's doing things in there that make you scratch your head and say, oh, I don't see that. So I'm going to try to make this understandable. It's not that tough. But the way he does it, I think, causes a lot of students to, if they're just reading it for the first time, they're scratching their heads and saying, huh? So here's what happens when you talk about radiation. If you have an antenna, one of the things you need to do before you can do anything further with it, and this is going to be an empirical calculation of trying to figure out or estimating the electric field. You got to know the current. So if you don't know the current on an antenna, you're screwed. All right, that's the trick. So with antennas, the first one they talk with is short dipole. Well, what is a short dipole? It's a piece of wire. Usually all these dipoles are center fed. It means the voltage is driving right at the center of the antenna. It's made of wire. It has a length L. All right. And that antenna has an L less than lambda over 10. That's our definition of short dipole. It means if you know the wavelength, then that antenna better be less than a tenth of a wavelength in free space, all right, for a short dipole. The reason I'm saying that, this isn't exactly true, but it's used all the time, and it is approximate. They're going to assume that the current is everywhere the same. It doesn't have a taper to it. That's not really true. I'm going to say that. See, he's assuming the current at this end is the same as the current right there. In reality, I'm just telling you this, your professor, the current, if you plot the magnitude of the current in this direction versus position on the antenna, it would taper down to zero at the ends, and it has to. What does your common sense say? If current's flowing in, whatever's flowing in is staying there or leaving, right? Right at the end of the antenna, you can accumulate some charge, but overall, it doesn't go to zero. I mean, you don't just have I flowing in and zip coming out and a charge ball puffing and, going up and down. Generally speaking, I mean, that would be like a capacitor. You get something like this. Actually, you'll probably get something that's more like this, where there will be slightly abrupt change, but it won't look like a constant value of current. If this is applying current up and down, even though we use that. I'll talk more about that as an approximation. So we assume that. Now, if you have a chunk of current, we don't right away go to the electric field. I'm going to just level with you. What we do is this, and you're not going to like it, but it's the way it is. We create something that's a non-measurable potential. There's a voltage that you can measure between 2 points, right? That's observable. I know the voltage, it's electrical pressure. Well, this is called the magnetic vector potential. You can't measure this, but it's used theoretically because it's so useful in the mathematical calculations. So write this down. If I have a chunk of current, I, and it's got a length BL, then there's a magnetic vector potential that's created called A. I'm going to get to this next time, but I just want to introduce you. So if I'm a distance R away from that little chunk of wire, doesn't matter, has nothing to do with angle or anything like that, just distance R away, there'll be a differential magnetic vector potential A equal to mu0 over 4 pi times I, right there, the actual I times dl vector. It has a vector sense, or the direction, same thing as IDL, and it will be divided by magnitude of R. It will be times e to the minus j beta r. Now, Dr. Wentworth's book does not have this. Well, it does and it doesn't. He has, where the heck is it? He shows us an equation 825 and 826, but he defines A in terms of the B field, which is true. But I want to define A separately. He starts in there. You're going to get confused in that one if you look at it. This is really the differential magnetic vector potential. Now, if you integrate over wherever the wire is, then you get the magnetic vector potential. The reason they do this is one thing. This is easy to get. Do you remember voltages were easy to calculate if you had charge distributions, right? They're scalars. On the electric field, you took minus the gradient of the voltage, you got the electric field. You all remember that? Well, it's the same way with this thing. If we get this, this has only one vector direction. It's this vector direction. On purpose, I didn't put more information than necessary. So that means if I have A, which would just be equal to the integral of dA, over whatever the length is, then I can get B by taking the curl of A. Now, I didn't prove that, I just stated it. It's absolutely true, mathematically true. The curl is taking, derivative operators on that vector quantity, and it will give you possibly three magnetic field components, really two. But getting B directly is oftentimes much more complicated and harder. This is easy, relatively speaking. Y'all with me, like voltage is easy to calculate. E fields aren't in general. But if you got the voltage, you can take the minus the gradient of the voltage and get the E field fairly easily. So that's the reason we use A. Next time I'll pick it up here. I'll give you something to chew on. But I wanted to mention this because some of you are going to read ahead and say, Dr. Vincent, this is pseudoscience. This is crazy. That's the reason I'm saying it. Hope you got something out of the lecture. If anybody's got questions, they can see me after class. Boy, that was quick.